everyone, my name is Natalie Lebaron. I'm a graduate student at UC Berkeley, and today I'm excited to present some recent work that I've submitted on the UV OIR emission from the most luminous known optical or fast blue optical transient, AT 2024 WPP. Fast blue optical transients are a recently discovered class of transients characterized by their fast rise-fade timescales, peak luminosities rivaling superluminous supernovae, blue colors, and for the most luminous of these objects, detected X-ray and/or radio emission. Due to their short timescales and lack of UV line blanketing, traditional supernova models cannot easily explain the emission from these transients. Most proposed progenitor models involve some sort of extra power source from something like interaction with a dense CSM or some sort of accretion onto a central compact object. However, due to the rarity of these transients, their fast timescales, and typically large distances, very few are well observed, and thus we do not have a good constraint on their intrinsic nature. This brings me to talk about the most recent well-observed LF bot, AT 2024 WPP, which was discovered about a year ago now at a distance of 400 megaparsecs. As I said, this is the most luminous LF bot discovered to date, peaking at almost -23 absolute magnitudes in UV wavelengths. This enabled us to collect very nice detailed multi-wavelength observations on this object, including the third LF bot optical spectral sequence that included 5 LRIS spectra, which especially contributed to discovering the spectral features of the latest epochs, which I'll get on the next slide. But over the first few weeks, this transient exhibited fairly typical LF bot behavior, being quite blue and featureless in the optical, and then eventually showing features of only hydrogen and helium, which are the only spectral features detected in LF bots thus far. And in our 3 different examples here, we do see quite different line morphology. So CSS over on the right-hand side has quite blue shifted broad features. 18 Cow, the prototypical LF bot, has much narrower and even slightly red shifted features. And in WPP, you can barely see them here, but in our final 3 LRIS spectra, we find this very interesting double-peaked line profile for its spectral features. So again, we see 2 components, one at a blue shifted velocity of about 6,500 kilometers per second, and another separate from the narrow host emission at around 0 kilometers per second. Again, this is very interesting. In the transient world, there are some TDEs that have claimed blue shifted features, but in general, this points to some very asymmetric ejecta geometry with multiple outflow components. Comparing the line parameters for WPP against the other 2 LF bots and TDs with and without blue shifted spectral features, we again see some very interesting things. So again, LF bots have only ever shown hydrogen and helium in their spectra. So that's more an analogy to TDs than supernovae. We also see that the velocities really don't change that much, especially for WPP, which again is not typical for supernovae at the very least. We also note that the equivalent width of WPP's lines is quite small, especially compared to the other LF bots, and they showed up much later in WPP compared to the other LF bots. This is consistent with WPP's much higher luminosity compared to the other LF bots. Speaking of the energetics, we compare blackbody properties of WPP in blue here to the properties of 18 Cow in red against their, in the vertical lines is the times at which 18 Cow in yellow and WPP in orange started showing their spectral features. And again, we note the very high luminosities for LF bots, WPP reaching 10 to the 45 ergs per second. This corresponds to a radiated energy of 10 to the 51 ergs, which already poses an issue for supernova models. But we also see the temperatures are quite a bit higher than is typical for supernovae, and it really does not cool. Both of these transients somewhat plateau around 18,000 Kelvin after about 20 days. In addition, we also find that these transients show mildly relativistic blackbody expansion velocities, just the blackbody radius over time. Which again, very interesting. In the near infrared, WPP spectra are very featureless, again, at all epochs, and generally follow the tail of the optical blackbody. We do see in our final near-infrared spectrum with Keck at 24 days, the hint of a spectral slope change in bar K-band, which at 30 days was conclusively shown to be the second ever detected LF bot near-infrared excess above blackbody emission. This is very interesting to see. 18 Cow was the only other LF bot to show this. No others were sampled in the near-infrared at these epochs. 18 Cow showed its near-infrared excess quite early on, within a few days of discovery. We find that WPPs was not there at 10 days, but unfortunately our near-infrared sampling is quite sparse. At the very least, LF bots showing near-infrared excess quite early on into their evolution, at least with 18 Cow, points to something interesting about the progenitor environment of these transients. Currently, our best ideas for where this near-infrared excess comes from is either some sort of dust reprocessing or potentially free emission in an extended atmosphere, in analogy to TDEs and stellar atmospheres. We do find that the luminosity of that near-infrared component at 30 days for WPP is consistent with the measured near-infrared luminosity for the cow at similar epoch. Our limit at 10 days is also consistent. But more interestingly, this graph shows a connection between the X-ray and optical components of emission. To examine that, we define this quantity L engine, which is just the sum of the soft X-ray luminosity and the optical luminosity, assuming that we have some central X-ray producing source, which its emission is reprocessed into the bulk of our optical emission. And we do see that as we get towards the orange shaded region, which again is where the spectral features started appearing for WPP, that the X-ray component becomes slightly more, a larger percentage of that engine luminosity than previously. This is in analogy to 18 Cow and was much more dramatic in 18 Cow as it was less optically luminous. To see this another way, we present the ratio of the X-ray luminosity to the optical luminosity in blue, as well as the X-ray luminosity over the near-infrared luminosity in shades of orange for both the cow and stars and WPP in the circles. So we can see that as we get towards those epochs where the spectral features emerge, again, 18 Cow in yellow, WPP in orange a little bit later, we see that that ratio approaches 1 near when those spectral features emerge. Another very interesting thing is at the top for the LX over near infrared ratio, we see that it's quite constant with time. This is very interesting. Our models for the near infrared emission don't really have a natural explanation for this. But it does suggest that there is some sort of connection between those two parts of the spectrum. Overall, our picture of the multi-wavelength view of WPP and LF bots in general is encapsulated in this schematic diagram that is presented in my postdoc Nana AJ's paper on the non-thermal emission from this transient. Basically, we have, again, some sort of central X-ray source, perhaps super Eddington accretion on a compact object, either neutron star or stellar mass black hole, which emits X-rays into some dense asymmetric medium that can reprocess the bulk of that X-ray emission into our optical emission. The X-rays can leak out through holes in this asymmetric medium. And as it expands, we expect that it gets more diffuse and reprocesses fewer of those X-rays, leading to potentially the ratio evolution that we see. On that note, I will put up my conclusion slide and invite questions.